All right, welcome back, friends. This is William M. Briggs to episode 37 of Uncertainty and Probability Theory, the Logic of Science. We're going to be doing simulations aren't what you think. Now, there's grown up a tendency, I don't say everybody does this, but a tendency of some people to imbue simulations with life. That is, we ask some source to generate random numbers or pseudo random numbers and put these into algorithms to give us approximations or results or approximations to results or something like this. And by the act of generating the random numbers or the random variables, we somehow give life to the results. We give them authority. We certify them with the randomness that is proper to probability. All of these ideas come from the idea that probability exists in nature, which we've already seen is not the case. So you'll hear people say, we're going to draw from a normal distribution and we're going to draw from a gamma distribution. Well, that doesn't make any sense in our way of thinking. What we can do is we can calculate numbers, we can calculate probabilities and so forth. There's no problem with that. And when simulations are used along those lines, there's little difficulty in interpreting them, as long as we're careful to understand that we're not giving probability any life. So when you hear nature draws, we're trying to find what nature is drawn from, and nature's probability distribution and all this kind of a thing. All that's malarkey. It doesn't exist. Nature doesn't have probability distributions. There are causes, there are powers operating with substances and so forth. And I realize we still haven't got the cause. I'm still trying to fit into uncertainty, moving along uncertainty. And I'll post this excerpt from the book online. I also have many other posts on this. I'll link them all below. All right, so James, this is James. I want to quote James. James discusses this. He doesn't do much along the lines of simulations, but he says, it appears to be a quite general principle that where there is a randomized way of doing something, then there is a non-randomized way that delivers better performance, but which requires more thought, That's what I'm going to try to demonstrate to you today. Now, I'm going to show you why people are even doing randomizations like Markov chain Monte Carlo is one of the more popular ones. There's all sorts of methods of simulations, but that's one of the more popular ones. And I'm going to show you the impetus behind it, the reason. And there's nothing wrong with its use. I want to stress at the very beginning, there's nothing wrong with using these to get approximations to numerical answers that we cannot get analytically. It's fine. However, there will be, as Jane says, if we could think more about these things instead of there's too much work in devoting time to these MC Markov chain Monte Carlo methods. That if we were to spend more time thinking about how to get better approximations to non-analytic results for certain equations that we have and so forth, we would be better off. And we would certainly be thinking better about how things are resolved. And all we're doing is coming up with approximations. So let's just come up with a very simple example here that's, textbook example of why people do simulations. Well, suppose I have some function. Here's my function that lives on the number line here. Well, I want to capture the area underneath this curve. Now, that's what integration does for you, gives you area under the curve. But this function is too difficult to integrate. There's no known analytic form that pops up. By analytic form, I mean we could solve this exactly. We apply the rules of calculus or something, or measure theory, and we come up with a formula which gives us, this is what the area under the curve is. Now, we might not be able to solve that by hand. We might have to come up with digital approximations to it or something, which is all fine. But in the absence of any of that, what we could do, it's very simple method. What we could just do is, this is y. of course, XY plot, and we could generate XY pairs. Just generate XY pairs randomly. Remember, random means unknown. Random means unknown. This is why the very language of simulations goes wrong immediately, because we know what the values of X and Y are going to be. It is we, after all, who are telling our computer or whatever source we're going to derive these things from to give us these pairs X and Y, but nevertheless we can. Let me use a color here as opposed to black. Maybe that'll help. Maybe it'll hinder. Let's see. All right, we'll just generate a pair. Here's a possible number we can generate randomly. Let's generate randomly. Here's another one. 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 We're gonna just do it in this range right here. We can just go on generating these pairs of numbers and so forth. In the end, I mean, you can imagine if I just keep populating this, I can take the number that are under, and I can test each one. Is this one under? I can evaluate this function. Of course I can evaluate it because after all, I've plotted it. Therefore, if I have a point here, I know at this value of X what the value of Y is. And I ask, is this point under, below, less than or equal to the function itself? And I just count up all of these dots that are under this curve, the number under, divided by the number total, and that gives us the approximate area under the curve. Simple as that. And nothing in the world wrong with this. I want to stress this one more time. There's nothing in the world wrong with this. And of course, here we could just numerically approximate it better just by taking points along this curve and getting a better idea. But where this is even more difficult is in multi-dimensions. In multi-dimensions and so forth, we have an equation with lots of parameters in it. We're going to meet models that have lots of parameters in it. It's very difficult to do these multi-dimensional sort of approximations like this, although not impossible. And these simulations allow us to put in pretty much general any form, especially when probability distributions are used because they have nice numerical properties, namely that they integrate to 1. And all this kind of a thing. The area, if this was a probability distribution, the area under this curve has to integrate to 1. That's what makes it a probability, and so forth. So we could do all kind of nice things like this, but simulations work. But we've gone kind of wrong when we start saying we're going to generate random numbers. Random again means only unknown, and we know what these numbers are. So the idea is to sort of turn a blind eye to their generation, and thus pretending we don't know how they came about, and therefore this result will be blessed in a probabilistic sense. Well, that's crazy. That's crazy thought, and I'm going to prove that to you. And again, I say this method does work. It will provide you reasonable answers. All right, as long as you keep in mind what you're trying to do is come up with an approximation to a function that's not analytic, no problem. I want to keep stressing that because I will be, and I have been accused of saying these methods, Monte Carlo and stuff, doesn't work. They do work, but we can come up with better methods with clearer thinking. So let's think about how this stuff uses. This thing, I could use any of a number of examples. I'm going to use what's called a Box-Mueller transformation. So how do random numbers, how are random, so-called the whole idea is just, you start saying this, and I catch myself saying, I'm saying random numbers. How are random, there are no, I have an example in the book, and I've used this example with you. I'm thinking of a random number between 1 and 4 right now. Can you guess it? You think about it. I'll tell you. I'll reveal my number now. I'll reveal my number later during this broadcast here. 2 of log of u1 times the cosine of 2 pi of u2, where u1, u2 are distributed uniform. u1 meaning they live on. So this is called a Box-Mueller transformation. We supply pairs of numbers, u1, u2, which live on 0 to 1, and these become a random normal. There's the random. We get ourselves lost in this conversation so quickly. The idea is we want to calculate the probability. Here's a normal distribution. We have values here, and we have the probability that z is less than the values given here. And here is a normal distribution. Here is the value 1. This thing asymptotes to 1. And here is negative infinity somewhere down over here. We can calculate the probability. So the probability of less than this value is going to be around 50% using this cumulative distribution function, okay? Now, so all we do is we supply a u1 and a u2 that live between 0 and 1, and we're going to get a value of z. And the idea is, almost all simulations are like this that use any kind of MCMC. They all have or start with uniforms. Uniforms meaning they live on 0 to 1. Because there's all kind of transformations that take a function that lives on 0 to 1 and can transform it to whatever complex probability distribution that you have, whatever mathematical form it may be. So they rely on these kinds of things. So they rely on first generating a number between 0 and 1. See that whole language, generating a number between 0 and 1 uniformly, randomly. We get quite confused, and I'm going to prove that to you. But nevertheless, we put a value of u1 and u2 in here, and we get a value of z. And a value of z is going to be somewhere along it's going to be somewhere along this curve. There's no problem with that. This is a direct thing. We could say that u1 and u2 explain or determine the value of z, right? That's what this function does. Any function determines the value of xy plot. The value of x determines the value of y in a standard simple function. Here, the value of u1 and u2 determine cause, we're talking about cause the value of z. That's all. We know what 2 pi is. We know what minus 2 is. We know what this is the natural log. We could easily calculate this kind of a thing. So once we have these numbers, we could do this. So now all computers have finite resolution. I hope that's not controversial. So let's imagine, although computers are better than this, let's just for the ease of writing this down, let's imagine that our resolution, the computer resolution, is 0.01. We can get numbers, real numbers. Real numbers exist on the continuum, which remember is infinitely larger than the infinite counting infinity, which we did last week. But our computer can approximate them to 0.01. All right. Now, since we need 2 numbers here, we could generate all conceivable pairs of u1 and u2. So that would be 0, 1 and 0, 1. Here's u1 and u2. We'd have 0.02, 0.01, 0.03, 0.01, and so forth up to 0.99. Notice we don't include the 0 and the 1. Here is our all possible things. This turns out to be 9,801 pairs. Just turns out to be this way if our computer takes this resolution. And if we do this, we plug 0.01, 0.01 in here. This gives us a value of z. We plug 0.02 in for u1 and 0.01 for u2. And gives us a value of z. And we keep doing this all 9,801 times. And we'll see. And I'll have a link to the blog. You have to look at the blog this week. I haven't figured out how to put pictures into this, edit pictures and graphs. I have to because we have a lot of graphs coming. I can't just wave my hands all the time in the lecture. As we get closer and closer to building models and we get to the real meat of this class, for the exciting part of this class for a lot of people. How do you do all this stuff in real life? We needed to do all this foundation. We absolutely need this foundation. You see, even me, I lapse into this random numbers talk, which is gibberish. We need to start speaking plainly. Now, if you were to do this at 0.01 resolution, I have this in the book Uncertainty. I'm going to have the excerpt up on the blog, wmbriggs.com, wmbriggs.substack.com, so you'll be able to all see this. And if you were to do this on this red dotted line here, which you could barely distinguish from the black, that's exactly what it looked like. And this black line is provided by an analytic approximation. In other words, I used R, and R has built in, it doesn't do a simulation every time it wants to reproduce this curve. It has an approximation to a normal distribution built in. It's not exactly analytic itself, but there's a nice approximation to it. And so we could do that already. See, there's already approximation. So in simple cases where we can come up with nice approximations to non-analytic functions, that we can do that, no problem. And now I can do this in my simulation approach. But notice, I just went through every conceivable pair. There's no repeats in this. There's no repetitions. I'm not drawing numbers from uniform distribution. I just went through methodically every possible pair. Every possible pair, and I got this. So I just calculated some numbers here. And now remember, our goal in any of these probability calculations is to answer questions put to it in plain language. So for instance, I might have wanted to know, the probability that z was less than -1 for whatever application I might have in mind. That depends on the evidence I give it. Well, in the analytic approximation built into R, that gives me 0.159. So the probability of z being less than -1 given the analytic approximation is 0.159. In this example here, where I used the resolution, I'll just call it this, R equals 0.01, I got 0.160. And if there's nothing magical about this particular resolution, I just picked it for an example. I could make it even cruder. I can make it into 0.5, and I get 166. And I did it just for fun, I did R equals 0.1. In other words, the resolution is every 0.05 increments, or every 0.1 increments, 0.1 and 0.1, 0.2 and 0.1, 0.3, so there's far fewer numbers available to draw this curve. But even with such a crude approximation as this, I get 0.172. Is that too far from 0.159 for you? It depends. There's no right or wrong answer to that, all right? That's the key here. Is 0.172 too far from 0.116? Maybe. It depends on the application. It depends on the decisions to which you're going to put this uncertainty model. All right? I don't know what those are going to be. Maybe this is good enough. And remember, any measurement that we make, any decision that we make is going to be, in science anyway, is going to have finite, discrete consequences. And so maybe that's good enough, but maybe it's not. I mean, this is kind of a trivial, stupid resolution. 0.1 is very crude. I mean, we could easily do this, and I did. And you could do this with other questions. I just picked -1, but you could do others and find out how good this approximation is. But you'll see this picture, and it's a pretty darn good approximation. In fact, I can't see the difference. They're all into the thousands place. The differences between this crude approximation with this 0.01 approximation and the analytic approximation to the normal never differs by more than a thousandth. At least I can't see that it does, and sometimes it's even closer than that. Depends on the particular value here. All right. So, all right, what's the big deal? Well, they wouldn't do this in a computer simulation approach. They would say, I'm going to generate random numbers. Well, how many do I generate? So just in the spirit of fairness, there's a thing called the R-unif function in R. R-unif function that allows you to generate random numbers. See, random numbers. Numbers between 0 and 1. Numbers between 0 and 1. There are no random numbers. The computer is picking them by an algorithm. And we turn a blind eye to that algorithm. They're just spitting them out one by one. In fact, you can make sure the computer starts and gives you the same sequence every time by setting something called a seed. I'm not going to go into any of that. I'll have that in the blog because that's not my main point. Anyway, I did this, and to make it fair, I want to calculate the probability of z less than 1. And I did the so-called random approach. And I picked, just in the spirit of fairness, I picked an example of 9,801 different pairs, just to make this the same length. And I did it 3 times. I got it 3 times. One time I got the answer at 0.162. One time I did 0.164. I did it a third time. I got 0.152. And then I did this whole thing 5,000 times. 5,000 times. In other words, I picked 9,801 pairs, and I calculated the probability z was less than 1, and I did the whole thing 9,000 times. And 90% of those answers were between 0.153 and 0.165, with an average, a numerical average, just a strict numerical average of 0.159, which turns out to be the right answer. But with some indication also of the uncertainty of that answer in this idea. I have also the idea of the uncertainty of the answer in this here, if I carried it through, just this right here. But the difference between this and this, even though they give me somewhat the answer, is I think I calculated it's somewhere close to 19 million calculations to give me this. 19 million calculations to give me this number. 19 million. There's just a handful of calculations to give me the analytic approximation. I don't know how many flops, floating point operations it is, but some trivial number. And this is, of course, 9,801, plus a little bit more to generate, to generate these things. A very small number compared to this 19 million, just to get this. So we see something with a little bit more thought, as Jane says, put into this, gives us a much better answer than it does making something we just blindly apply these simulations, thinking about random numbers and all this kind of a thing. Now, can I do this in higher dimensions and so forth? Certainly I can. I can generate, this is more or less just like generating a grid. In that one example I gave, I would be just generating a grid, if you like, of points above and below whatever function we're trying to approximate, and I just increase the number of the grid. It's inefficient in a way because I'm generating a lot of wasted space up in here and so forth. So what people do is they come up with functions that we do have analytic approximations to, which are better known, and we only have to generate stuff in between here and under here. There's all kind of tricks that can be done to get answers, because in the end all we're interested in is this. This is what we want to know. We want to know the and it's not being blessed. We want to know the probability that z is less than 1, because this was our question, or whatever question that you might have had. That was our question we wanted to answer, and we came up with we can come up with approximation. No matter what, we have an approximation to it. This is the analytic approximation. This is the approximation with a resolution of 0.01. Those are good enough for most applications, I would say. It's up to you how good you want to make this. It depends on what exactly you're doing with it, again. In the end, though, this simulation, the MC stuff, is not giving you anything extra. It's only giving you this. It might be able to do it where this is going to be more inefficient. This kind of approach may be more inefficient if you have a lot of dimensions and it's very sparse and all this kind of a thing. Absolutely. But you're not buying anything. You're not gaining anything in the correctness of the results by calling upon random numbers and so forth. There's absolutely nothing going systematically. There's nothing in the world wrong going systematically. There's no reason why I have to start with a 0 and then a 0.7 and a 0.4 and a 0.1. None of that. None of that is necessary. I could have gone in any simulations I'm going to do, however many uniforms that I want to put into formulas like this, how many U's I should say, into formulas like this. I could always start and do a grid-based thing and come up with all unique combinations. There aren't going to be anything else. And this 5,000 times of 9,801 things, there's going to be many repeats of 0.01 resolutions. I don't need to do that. I don't need to waste all that computational effort and so forth. I can just do what I want. Again, we're discussing the philosophical import of all of this kind of a thing. However you get to the approximation in the end, if you're answering the question you want to answer, it's fine. I don't dispute using the simulation methods to get that, okay? But it always has to be realized it's only done because it's an approximation. It's not giving you anything beyond an approximation. It's not more correct. I mean, this analytic approximation they already have built in here is better than any simulation method just because it's a better approximation. This number here doesn't give us anything more important because it used random numbers, and this is supposed to be a normal distribution which somehow lives in nature and so forth, which is an absurdity. There are no normal distributions in nature. There are things that have causes, and we haven't still got the cause, I know. And I realize I didn't want to forget the most important part, because here when I'm saying that U1 and U2 determine or cause the value of Z, we still need to talk about information theory. That's what we're going to do next time. True randomness. What does true randomness mean? We're talking about all these kind of random numbers. None of these numbers are random, unknown, but there are things in the world that are unknown that we do not know the causes of. Remember, random means unknown cause or unknown value. And we don't know the explanation for some things. And that's absolutely true. We don't know the explanation for some things and can't know. And we do bump up against a fundamental uncertainty in the world beyond which our intellects cannot peer. And that's well thought out in information theory, which is just exactly the same as probability theory by another name. There's no difference. And we'll see that next time. For now, I'm going to give you lots of material to read and so forth. And you can play with this. I have code and everything. You know, it's easy enough to do to convince yourself if you're not otherwise convinced. That's it for now. Thank you very much for listening. See you next time. Oh, by the way, there he is. The links will be down there, wmbriggs.com, wmbriggs.substack.com, either one. Thank you for listening.